These notes are on special right triangles. We have worked during the course of this year with finding the missing sides and the missing angles for right triangles using Pythagorean theorem and using trigonometry. And it turns out that we also found out that any triangles with that corresponding angles are congruent are similar triangles, which means that their ratios of the sides are equal. They are the same sort of proportion blown up or shrunk. And so it turns out that two triangles that we work with very often play a special role in trigonometry. And we'll look at them this year, but really they'll come into play much more heavily in Math 3. So when we look at, first we'll talk about 45, 45, 90 triangles. When we look at 45, 45, 90 triangles, I can find the missing sides of this triangle only given one side. So that's unusual. With trigonometry, I would need to either have, I can find the missing sides without using trigonometry, even when I'm only given one of the sides. And that is because 45, 45, 90 triangles are isosceles, which means that this side, if this side is 8, that this side is also 8. So I now can find x, or my hypotenuse. So 8 squared plus 8 squared equals x squared. 64 plus 64 equals x squared. 128 equals x squared. Square root of 128 equals x. And that turns out to be 8 square root of 2. The same can be done when I'm given just the hypotenuse. And again, that's because the 45, 45, 90 triangle is an isosceles triangle, meaning that these two lengths are the same length. So now I have x squared plus x squared equals 10 squared, 2x squared equals 100, x squared equals 50, x equals the square root of 50, x equals 5 root 2. So you'll notice that in both of these answers, I have a square root of 2 coming up. And the reason for that is it actually turns out that the ratio of the sides of any 45, 45, 90 triangle are always in this proportion. They are always in the proportion x, x, x root 2, where x and x stand for the legs, and the x root 2 is the hypotenuse. So let's look at a couple examples. And to remind you, of course, that when we're talking about the 45 and we're talking about its sort of corresponding leg, it's a cross. So the hypotenuse is across from the 90-degree angle, and the congruent sides are across from the 45-degree angle. So let's look at a couple examples. We're asked to find the missing legs of the following triangles. In our first example, we're asked to find we're given the hypotenuse. So because this is a 45, 45, 90 triangle, my ratio is x, x, x root 2. I then know that the 7 root 2 is my hypotenuse, so that is this piece, which means I can write x root 2 equals 7 root 2, which means x equals 7. So now I know the sides are 7, 7, and 7 root 2. In my second example, I'm given a leg. So again, it's 45, 45, 90 triangle, so I always start by writing my ratio. In this case, I'm given one of the legs, so I'm given the x. So x equals 8 root 2. So I know these two, so I can say the sides are 8 root 2, 8 root 2, but now I need to find the hypotenuse. So I know what x is. So now I can replace x with 8 root 2. So I would have 8 root 2 times root 2. Right here I replaced the x in the x root 2 with the 8 root 2. But I can simplify this. This is 8 square root of 4, which is 8 times 2, which is 16. So there are the three legs of that particular triangle. Now we have a second we have a second triangle, special right triangle, that we often deal with. This one is the 30, 60, 90 triangle. Now, when you were doing the trig section where you were finding the missing sides, you probably noticed, or if you didn't, you should, it is possible to notice that the legs of a 30, 60, 90 triangle also come in a particular proportion. What you would have noticed more easily is the proportion between the short leg, that's the leg opposite the 30 degrees, and the hypotenuse. That it's always going to be, the hypotenuse is always going to be double the length of the short leg. Now, very often when you were doing these problems, because you were using a trig function, you would have gotten a decimal answer for the side opposite the 60 degrees, the long leg of the triangle. But it turns out that that answer is equivalent to whatever the short leg is times root 3. So let's look at a couple examples. In our first example, we are given the hypotenuse. So it's a 30, 60, 90 triangle, which means I am going to start by writing my ratio, x root 3, and 2x, where x corresponds to this short leg, the one opposite this 30 degrees. X root 3 corresponds to the long leg opposite the 60 degrees. And the 2x corresponds to the hypotenuse opposite the 90 degrees. So the information I'm given in this case is the hypotenuse. So I can say that 2x, my hypotenuse, equals 14, which means x equals 7. So the sides are 7 inches, 7 root 3 inches, and 14 inches. Once I knew what x was, I simply plugged that in for the long leg, the side opposite the 60-degree angle, to get my 7 root 3. Last example. In this example, they don't actually label the third angle, but we know that the three angles in a triangle add up to be 180, and that if this is 90 and this is 30, this one has to be 60. So they give us a 30, 60, 90. So my ratio of x root 3, and 2x. In this case, they give me the answer, the number that's across from the 30-degree angle. So they give me the short leg. That's a short leg, so x equals 2. So then we have the sides are 2 root 3, and 2 times our x, so 4.